We'll just consider example 1, where we have a mu A741 op-amp in an inverting configuration with a gain of 5. That is, our output voltage per input voltage is equal to minus 5. We want to model this first, treating it as an ideal operational amplifier, and then we want to model it using our offsets model. For us to begin, for an ideal operational amplifier, we're going to assume I1 and I2 are both equal to 0. I1 is our current entering our inverting terminal, and I2 is our current entering our non-inverting terminal. We're also going to assume V1 and V2, our voltage potentials at our inverting and non-inverting terminals, are equal. Since V2 is equal to 0, V1 is also equal to 0. Now, to relate our input and output voltage, we want to apply Kirchhoff's current law at node A. Thus, we can relate our input voltage to our output voltage. Our source current is entering node A, while I1 and IF are exiting node A. I1 is equal to 0 by our ideal operational amplifier equations. Now, if we express KCL in terms of Ohm's law, we have Vin minus V1 per 10 kilo ohms, which is equal to Is, is equal to V1 minus Vout per 50 kilo ohms, which is equal to If. Since V1 is equal to 0, we can solve for Vout simply as minus 50 per 10 Vin, or minus 5 Vn. Now, if we are to model this using the offsets model, we can no longer set I1 and I2 equal to 0. Rather, we're going to have to include our biased current sources IB1 and IB2 and our voltage offset VOS, as shown on the schematic to the left. Within the offsets model, I1 is going to be equal to IB1 and I2 is going to be equal to IB2. Our offset voltage, VOS, is going to be equal to V1 minus V2. Now what we recognize is we have 4 independent sources, Vn, IB1, VOS, and IB2. To solve for the behavior of our circuit, superposition will be the simplest method. That is, we are going to treat each independent source individually while disregarding the others. To disregard the others, we are going to short our voltage sources and open our current sources. Now, considering Vn, we see that this is the same configuration as our ideal op-amp. That is, IB1 and IB2 were opened and VOS was shorted. Thus, I1 is equal to 0, I2 is equal to 0, V1 and V2 are both equal to 0, and our gain is equal to minus 5. And thus, our output voltage is equal to minus 5 Vn. For VOS, we are going to short Vn and open IB1 and IB2. And we recognize this is a non-inverting op-amp. Thus, we will apply our equations. I1 is equal to I2, which is equal to 0 within our system because we do not have biased current sources. And V1 is equal to V2, where V2 is equal to VOS, our voltage offset. Now we can apply KCL at node A to relate our input currents and output currents. Is is equal to I1 plus If, where I1 is equal to 0. If we apply Ohm's law to our KCL equation, Is is represented as 0 minus V1 per 10 kilo ohms, and If is represented by V1 minus Vout per 50 kilo ohms. Or if we express this in terms of Vout, Vout per 50 kilo ohms is equal to V1 per 50 kilo ohms plus V1 per 10 kilo ohms. Or Vout is equal to 6 VOS. Thus, we have a non-inverting op-amp. Our gain is positive 6 within our system. Next, we can consider our biased current source IB1, where we short Vn and VOS, and we open IB2. Now in this configuration, we recognize that V1 is equal to V2. And we also recognize that I2 is equal to 0. Thus, when we apply KCL at node A, we have Is, our current source that would be coming in from V1 if it were there. And we have I1 exiting node A, that goes from node A to our inverting terminal. We have IB1 exiting node A going towards ground, and we have IF running through our 50 kilo ohm resistor. If we apply Ohm's law, Is is equal to 0 minus V1 per 10 kilo ohms, where V1 is equal to 0. And this is equal to IB1 plus I1, which is equal to 0, plus IF, which is V1 minus Vout per 50 kilo ohms. Or Vout is equal to IB1 times 50 kilo ohms. Last but not least, we consider IB2. In this particular situation, we recognize that V1 and V2 are equal, and V2 is equal to 0, and I1 is going to be equal to 0 in this particular configuration. Now if we apply KCL at node A, we'd have IS, our source current, that's coming from where Vin would be, is equal to I1 plus IF. If we apply Ohm's law to this equation, IS is expressed as 0 minus V1 per 10 kiloohms, and this is equal to I1, which is 0, plus IF, or V1 minus Vout per 50 kiloohms. Vout is trivially found to be equal to 0. Now we can sum the terms from each of our independent sources. Vout is equal to minus 5 Vn plus 6 Vos plus IB1 times 50 kiloohms. Now, if we consult table 6.7-1 within our text for mu A741 op amp, we can use typical values for our offset voltage and bias currents. That is, our offset voltage has a typical value of 1 millivolt, and our bias current has a typical value of 20 nanoamps. If we substitute these values into our expression for output voltage, we'd have minus 5 Vn, which is responsible for input voltage, plus 7 millivolts. This 7 millivolt change takes into account our offset voltage and bias current. And we see this is a pretty small value in comparison to our input voltage. If we use the maximum values as reported on page 228, our output voltage is going to be equal to minus 5 Vn plus 55 millivolts.